In today's video, we will be talking about the AlexNet architecture from 2012. AlexNet is a convolutional neural network which was trained on the ImageNet dataset, which contains over 15 million images and 22,000 classes. So this was quite the difficult dataset, and the authors showed that convolutional neural networks, they can in fact scale to these kind of datasets. And I've drawn here the architecture of AlexNet, and I won't be going into too much detail about all of these individual layers, but suffice it to say that as a high-level overview, the architecture consists of two parts. On the left part here, we have the feature extractor, and on the right side, we have the classifier. And the network itself is actually not that complicated. I would say the most complicated part is the so-called local response normalization. But other than that, most of these are standard components that you would find in any machine learning library. For example, things like convolutional layers or max pooling layers. These are very typical in libraries like PyTorch or TensorFlow. So the main novelties of AlexNet were that they were using ReLU instead of sigmoid, and showed that using ReLU not only makes the network more performant, it is also much faster to train on because ReLU is such a simple operation. They were also using 2 GPUs to train AlexNet, which at that time was insane, and they wrote a bunch of custom CUDA code to make it work. This part we will actually skip because, well, I only have one GPU, and the one that I have, which is a 3090, is much faster than what they had back then. Also, they invented this local response normalization, which is, in my opinion, the most complicated part of the network, aside from the CUDA code, of course. And we will cover this in just a few moments. And then they used max pooling, for which they used a stride of 2, and that was also kind of new at that time. And aside from these architectural changes, they also augmented the data a bit, because you see these ImageNet images have varying image dimensions. So what they did is they took the image and they cropped it to a 256 by 256 image. Then they selected a random 224 by 224 portion of the cropped image. Then they randomly flipped the image horizontally, and they also applied some PCA color augmentation, which is like applying kind of filters but keeping realistic colors in mind. And finally, they also used dropout to prevent overfitting. Now, most of these components, aside from maybe the local response normalization and the CUDA code, were already known at that time. But the combination of everything is what in the end wrote history. So we will be implementing AlexNet in JAX by using the Equinox library. And the reason for that is, for one, AlexNet has been around for quite some time, and there are also quite a few tutorials out there that implement AlexNet in PyTorch or TensorFlow, but not so many that do it in JAX. So this video will fill that gap. And to do that, we will be using the standard machine learning pipeline, where you first get the data. For this, we will be using TensorFlow datasets. We will pre-process the data, kind of in the same way that they did over here, except for the color augmentation. And the dataset that we will be using, it won't be ImageNet because it would take way too long to train AlexNet from scratch on this dataset. We will be using something called cats versus dogs, where you have to classify an image if it's a dog or a cat. We will split the dataset into training and testing datasets, and then we will define the model. In our example, of course, the model is already given, so we won't change it. Actually, we will use it exactly as is. And most tutorials, they actually don't use the local response normalization. They go straight to batch normalization, which is better than this local response normalization. But in my opinion, if you want to implement AlexNet, you have to implement it using local response normalization, even though it has been largely overshadowed by batch normalization. Then we train the model, and then we evaluate the model. And if need be, you would refine the model. But in our case, that part will be skipped. And then we're done. So I briefly wanted to go over some of the layers in the AlexNet architecture before we actually get to the code. And starting with the convolutional layer, I was thinking initially of making quite the in-depth tutorial on the convolutional layers, but there is an amazing video from 3 Blue 1 Brown that explains convolutions using really fantastic animations. So I would highly suggest you go and watch that video and then come back here. But basically, when you're talking about convolutions, you have, for example, two lists of numbers like A1, A2, A3, B1, B2, B3, and you want to take the convolution of these two lists. And the convolution of these two lists will generate a new list. And the way that you would do it, of course, you would be using probably NumPy or PyTorch or whatever. You won't be doing this by hand, but the way it is done is you flip this second list by 180 degrees, put that over here, and then multiply the overlapping values, and then shift this list by the amount of stride that you define, for example, 1 to the right. So in this example, for the first index of the new list, since only A1 and B1 are overlapping, you multiply those, and that is the first index of your result. Then you move this list one step to the right, such that A1 and B2 are overlapping and A2 and B1 are overlapping. Then again, you take the product of these and then sum them together. So you have A1 multiplied with B2 plus A2 multiplied with B1, like this. And you keep shifting this second list over to the right until no values overlap. And when you do that, you kind of get this triangle shape, and the result is a new list of numbers. And if you watched the 3 blue 1 brown video, you will know that you can use convolutions, for example, to add to probability distributions or to compute the moving average. For example, here, if B1 is 1/3 and such as B2 and B3, they're also 1/3. If that is the case and you compute the convolution, what you actually are computing is the moving average. And again, I would suggest you go and watch this video to see all of this beautifully animated. But other things you can do with convolutions are, for example, edge detection and blurring. And this might be a little bit out of the blue. What do these have to do with these ones, and how do these relate to convolutions? What you see over here was the one-dimensional case, but you're not limited to only one dimension. And in this example here, you have a two-dimensional list, which is basically an image or a matrix. And each pixel of your image can be, for example, a vector consisting of 3 numbers, which represent the red, blue, and green values of a pixel. Or if it is a black and white image, it can be either 0 or 1. On the other hand here, you have the other list, which is also two-dimensional. And the name of the other list is a kernel. So in this example here, this would be the kernel. And depending on how you choose the values of this kernel, you can have special effects that you get on your outputting image. For example, I could choose a kernel such that when I take the convolution of my image and my kernel, that only the vertical lines would remain. And the way you can visualize this is by taking this kernel, again flipping it by 180 degrees and putting it over here, and then we'll move it along by a stride, and then multiply this patch of the image with your kernel. And depending on how I select this kernel, I can make it such that only the vertical parts remain. And when I do that, and when I have this special kernel that detects these vertical lines, and again, you should watch 3 blue 1 brown's video for a much better example of this, then with that kernel, the convolution would yield this image where everything is gone except for the vertical part. I could select also a different kernel where I would get a kind of blurring effect. If each value in my kernel was 1/9, then if I take the convolution, I get kind of a blurry effect like you would get if you take off your glasses or something. And in the context of convolutional neural networks, you wouldn't handcraft these kernels to find specific patterns or features. These kernels would be the weights of your convolutional neural network. You would let, through training and data, you would let the network decide on what these kernels will be. For example, over time, your network would just naturally find kernels that are very good at, for example, detecting faces or edges or curves or something like that. And there are great examples on the internet where you can actually see these kernels and what they detect. So that's quite fantastic. But basically, your network would learn these kernels. And this is a good moment to talk about local response normalization. And I have the formula for local response normalization over here, but it's not really clear what this normalization even does. And in my opinion, the authors unfortunately didn't really make a great job of explaining what it is. So I'll do my best here. So as a high-level overview, what they want to achieve with this normalization is to force the network to learn kernels that detect other features. Because you could have the scenario where, let's say, you have n kernels, that your first kernel is very good at detecting vertical lines, and so is your second kernel and third kernel, and so on. And for example, the last one could be very good at horizontal lines. In this scenario, this would be a waste of computational brain power, if you want, because you don't need this many kernels to detect vertical lines. It will be much better if only one kernel detects vertical lines and the other kernels detect other features like faces or curves or something like that. So what they want to achieve with normalization is to force the network to, well, to not do this, to punish the network for having kernels that activate on the same feature. And the way that they do it is they look at the activation of the convolutional layer, which means the output of the convolutional layer, and see if this filter has a high output similar to its neighboring filters. And just as a quick recap, whenever you define a convolutional layer, you have to give it the kernel size, which would refer to the dimensions of your kernel. And you also have to define the number of filters. For example, your input image might have 3 filters or channels, which is the red, blue, and green channel. But then you can define the number of output channels or filters. You're not restricted to have only one filter. You can define as many as you want. For example, here you can define n filters. In that case, you would have n kernels, each of which has the kernel size. And these would make up a single convolutional layer. So what happens here is we look at a particular filter and compare this filter to its neighboring filters. And if all of them have a similarly high output, meaning that the underlying kernels all have learned kind of the same feature, if that is the case, then we want to make this number smaller. But what does it even mean to make this number smaller? What does it do in the end? Well, if you make this number smaller, if the neighbors have similarly high values, when you do that, you make the neural network performance worse. That is, you increase the loss. And why does it increase the loss? You have to think about it from this perspective. Imagine that you get a kernel and afterwards you get this image where it is pretty clear that it detected a vertical line. But now after the normalization, because all the neighboring kernels have also learned to detect vertical lines, that after the normalization, this vertical line is kind of gone or very blurry, and it's not immediately obvious what this kernel has even detected. And because of this, the confidence of what this even is decreases, and with that does the precision of the network, because now the classifier is not even sure what it's looking at. And this will make the performance worse. And as a rule of thumb, whenever the performance of a network gets worse, the network will do everything it can to avoid that. So through gradient descent, it will learn to avoid the thing that made its performance worse. And what did make the performance worse? Well, if all of the kernels, they learned the same feature, and learning the same feature yields worse results, then the network will avoid to do that and force each of these kernels to learn a different feature. And this is quite a long-winded explanation of what local response normalization does. So as a summary, basically, they want to force the network to make sure that each of these kernels learn a different feature and not all of them learn the same feature. That's what they want to achieve with this normalization technique. The last 2 layers I want to go over before we start with the code is max pooling and dropout. So for max pooling, you have to define the window dimensions. In this example, it's 2 by 2, and you also have to define the stride. For AlexNet, they used a stride of 2. So what happens with max pooling is you get your input matrix. In this example, it's a 4x4 matrix. You create a 2x2 window, what you defined with the max pooling layer, and put that in the top left corner of your input matrix. Then you take this patch of your input matrix and look at the maximum value of this patch, which is 9 in this example, and put that here in your resulting output matrix. Then you move this window based on the stride that you defined to the right. Since we defined a stride of 2, we take this window and move it 2 units to the right. So that will be here. And then you look at this patch and take the maximum value again and put that over here. Next, you take your window, move it down to the bottom left corner, and once again look at the maximum value, which is 16. You repeat that process and take your last value, which is 10 for this window, and put that over here. So max pooling is actually a very straightforward and simple layer. And as you can see, we don't have any trainable weights. This is just a simple operation used to reduce the dimensions. Because we started here with a 4x4 matrix and ended up with a 2x2 matrix. And this has two advantages. For one, it makes your network focus on the most important pixels if you're dealing with images, because this could be your input image with lots of pixels, but you actually only want to focus on the most important ones, or the ones that have the highest pixel value because they are the most relevant ones. And the other thing that max pooling helps with is to tackle the vanishing gradient problem. Because if you have a very large network, then while the layers towards the end get rich gradient information, as those gradients propagate towards the start of the network, the beginning layers won't have any gradients left to learn anything. So by using max pooling, you're making the network smaller and therefore giving the beginning layers of your network much greater gradient information. And this helps to tackle the vanishing gradient problem. The last layer I want to talk about is dropout. So for dropout, you get your input matrix here, which is typically the weights of some layer. You define a probability. In this example, it's 0.5, and it's also the one that they used in AlexNet. And with this probability, you turn off some of these neurons in your weight matrix. And the way it is done, you define a mask of the same size containing zeros and ones, and you multiply your weight matrix with this dropout matrix or mask. And when you do that, you will in fact make the network more robust. But why does it make it more robust? Well, by randomly turning off some weights, you are forcing the network not to rely too much on a single feature, because that feature may be randomly gone. So you have to build in some redundancy, and that makes the network more robust. One thing to note is that you use dropout only during training and not during inference. And now that we have talked about most of the relevant layers, we can now jump to the code and implement AlexNet. Okay, now that we have talked about some of the layers on a high level, it's time to implement AlexNet in JAX. And to follow along, you have to install these libraries. And what you see here is not a Jupyter notebook. It's a library called Marimo or Marimo. I'm not exactly sure how to pronounce it. It's this library right here. And I've been using it for quite some time now. And I really have to say that I enjoy working with this library much more than with Jupyter. So I would highly suggest you go and check out this library. The team is incredibly fast at fixing issues. So I actually had one tiny issue with this notebook and I posted it on their GitHub repository, and almost immediately they fixed the issue, and the next day they also released a new version. So within a day they fixed my problem. So huge shout out to the team. I think they're doing incredible work and you should definitely check out this library. So to get started, I usually import all of the libraries on the very first cell. And perhaps one thing that's not clear what it is this CLU library, which stands for Common Loop Utils. And it's a library from Google to display metrics and stuff like that during training. So the first thing we do is we get the dataset, and for that we use TensorFlow datasets. And we have to define the name of the dataset. It's cats versus dogs. And then we can use their, in my opinion, pretty neat split API where we can get the training data and the test data by using this slicing operation. And there's quite a few things you can do with this split argument, and you really have to check out the documentation to see all the things you can do with this. We also set with info to true, which will give us the info object, and we also set as supervised to true, and by doing that we get a supervised pair or a tuple containing the features as well as the label. And when we have a look at the information, we can see here it's cats versus dogs, and we can also see the dataset size at 1.04 gigabytes. It's actually quite small, and also other kinds of information. We can also have a look at some of the images in this dataset. So what we can do is we can use this take function, which we use to get 10 rows from the training dataset. We turn those into a list and then take the third element of that list. And we can also use the marimo.image function, which will render this image. And as you can see, it's a dog, and the image shape is 493 by 503, where 3 is the channel size, and this is the height, and this is the width. Furthermore, you can see that if the label is 1, then it is a dog, otherwise it is a cat. For example, if I take the next image, then now we get a cat, and the image shape is now 375 by 503. And surely you have noticed that the height of the image has changed. So this means we'll have to write a function that resizes the image to a constant 224 by 224 dimension, similar to what the team did with the ImageNet dataset. We can also use the treescope library to render this array, and this will take a moment, but once it is done, we can actually see the array that creates this image. And if we zoom out, then you can see here some of the features of the dog. For example, here, this is the nose, these are the eyes. The image is flipped by 90 degrees, but this is actually what this image looks like in terms of a NumPy array. And if we zoom in really far, we can see here the actual values of the image. For example, this pixel right here has the value 78. And 78 is a pretty big number in the context of machine learning. So typically you would normalize this image and make these values much smaller. And to do that, we define two functions. The first one is normalize, so we get an image and a label as input. The image has the dimensions height, width, and channel, which is exactly what you have over here. And you return a tuple of the same dimensions. But what you do is you cast your image to a float and then divide it by 255. And when you do that, you normalize the image and make these numbers much smaller. Then we also have to resize the image. And for that, we will use this resize function. And we resize the image to 224 by 224. And also we transpose the image. And we do that because in Equinox, and I think also in PyTorch, the convolution layer actually expects the first dimension of the input matrix to be the channel. So what we want to do is put the channel dimension in the first position, and we can do that using this transpose function. Then over here, we define the shuffle value and the batch. And the shuffle value is a number which you could theoretically set to the length of the training dataset, but that will take up quite a lot of memory. So you divide it by 1000 to make it a little bit smaller. You can think of it as kind of like a seed, or that's how I like to think about this. And of course, the batch size is, well, the batch size. Then here we can create the datasets, and we use this as NumPy function from TensorFlow datasets, which will convert the TensorFlow dataset into a NumPy array. And this function expects a TensorFlow dataset as input. So here we have our TensorFlow dataset, which is trained. We call the map function and pass it the function that we had defined earlier as input. And this function will return another TensorFlow dataset, but this time with the normalized images. And on that new dataset, we can call the map function again using the resize function. We can shuffle the dataset using the shuffle function. Again, all of these return a TensorFlow dataset. Then we can call the batch function, which will split the dataset into these batches, and then also use finally the prefetch function. It's not so important what the prefetch function does. It basically just makes working with these datasets a bit more efficient. but it's not really relevant for us right now. We also do the same thing for the test dataset, except of course the shuffling, because you don't need to shuffle your evaluation dataset. We can now start with implementing the AlexNet model, and most of the components of the model are already available in the Equinox library, except for the local response normalization. So we start by defining this layer right here. And just by looking at the code, it's not immediately obvious what is happening, because here we have this pad function and we have this body and also this dynamic slice and dimension. But it will be much easier to understand once I go over all of this step by step and explain what's going on paper. So I've written here the equation for local response normalization, where the output is B, and then that is equal to A divided by something something. And A refers to the output of the convolutional layer. And this I over here, that is not an exponent, it's the kernel index. So what we have here is some kernel divided by something something. And as stated before, a convolutional layer, specifically a two-dimensional convolutional layer, which is what we use for AlexNet, you have n kernels, where each kernel is a 2D matrix. And then, of course, each matrix has this y and x direction. So instead of drawing it in 2 dimensions like this, I will now use these lines instead, because we won't be dealing with individual indices of the matrix. We'll do matrix operations on the whole matrix and not on individual indices, because that would be crazy. And if we have a look here at the equation, we can see that we care about a specific range that goes from this max term to this min term. And to quickly reiterate, the thing that we're trying to do is to look at a specific kernel, and if the neighbors of this kernel have high values, then we want to make this kernel smaller. And when I say neighbors, then this is what I mean. And the neighbors that I'm referring to, they are defined by this n term. So the range we care about goes from this maximum of 0 or I minus n divided by 2. This is not a real math notation, but in Python, when you do a double slash, you get an integer division, which is what I wanted to simulate here with these double lines. So this is really an integer division. And as an example, 5 integer divided by 2 gives you 2, because 5 divided by 2, that's 2.5. And it will be rounded down to the closest integer, which is 2. So the range we would care about goes from 0, because we don't want to have negative indices, or I minus n divided by 2, all the way to n minus 1, that's the last kernel, or I plus n divided by 2. And as an example here, if capital N, which is the number of kernels, is 96, the kernel we care about, I, is equal to 6, and n is equal to 5, then the range we would care about is 6 minus 5 integer divided by 2, all the way to 6 plus 5 integer divided by 2. Because in this case, the minimum of these is going to be this half, and here the maximum is going to be this half. So the range that we care about goes from 4 to 8. Or in other words, it's 4, 5, 6, 7, and 8. That's the required window. So if we have our kernels over here and we care about this kernel right there, then what we want to do is to get a slice of our array that contains this window. So we get the kernels 4, 5, 6, 7, and 8. And once we have those kernels, we can just simply do the operation that is stated over here, where we square that and then take the sum. And then once we have that, we can multiply it with alpha, add k, which is a bias on top, and then take it all to the power of beta. And to get this slice of our array, we can use the dynamic slice function from JAX. But don't let the name fool you. Although it says dynamic slice, the only thing really dynamic about this function is the start index. The input array that you give must be static, and so must be the slice. In our case, the slice will be constant. It will be n, or in this example, it will be always 5 kernels. The input array will also be constant, because that will be our convolutional layer. But the start index can change, because it depends on whatever the value of I is. But this gives us two edge cases. What if I is equal to 0, and what if I is equal to n? Well, if I is equal to 0, then what would happen is that we only have 3 kernels, but we actually need 5 because, well, the slice must be static. So in order to remedy that, we need to do padding. So over here, where our index is I equal to 0, then we need 2 additional kernels, both initialized to 0. And when we do that, we once again get our full static slice. And the math will still work out because if you simply add 0 matrices to this, then the end result won't change. And you do the similar padding at the end as well. And if we go back here to this statement where I said that all of these are independent operations, what I mean by this is the output of one operation where you say, for example, I is equal to 2 or whatever, once you do the computation, that doesn't depend on anything else. For example, if let's say you are at index 6, you do this computation, you get this output. Then if you want to compute the output for kernel 7, you wouldn't take the updated value here at 6, you would still use the original array. And in that case, these operations are independent. Or the way you would implement this, perhaps if you weren't using the vmap function, is, for example, by iterating over the input array. So you would have maybe a for loop where you go from I equal to 0 all the way to the last kernel and then do this operation for whatever index you're at. Or another way would be, because you noticed, well, I don't actually have to loop over this array. Perhaps I can just start 10 threads and say, for example, to thread number 6 that you should only care about the situation where I is equal to 6 and do that operation only for that specific case. And once you're done, you just wait until all the other threads are done, and then we can stack the results and get the final output. And that's exactly what you do with the vmap function. And that is how you would implement local response normalization in JAX. So now let's go back to the code and show how all of this is implemented in Python. So over here in the code, we have to define the hyperparameters, and all of these are static operations. In fact, this whole layer does not have any trainable parameters. In the init method, we save all of these hyperparameters because we'll need them in just a moment. And in the call function, we get our input array x, which has the shape channel, height, and width. And the array that we return will also have the same shape. So first we get the number of channels from the shape of our input array, and then we need to do a padding operation. So the way this padding operation works is you give it your input array and then define the pad width. And there are many ways to define the pad width, and one of those is to define the padding for each dimension. So since we have 3 dimensions, C, H, and W, or the channel height and width, we will have 3 tuples. And because we only want to pad on the channel dimension, we only define the padding value here in the first dimension. And we pad it by n integer divided by 2. And we pad that amount in the beginning and also the same amount at the end. For the height and the width, we don't want to do any padding. And the output of our operation will be coming from this vmap function. We pass it the body as input, and I'll talk about that in just a moment. And for the body, we need to give it the index that it should care about. So this arrange function will create a vector that goes from 0 to 95, and each of these values from this array, so 0, 1, 2, 3, etc., will be given to this body function. So we will have, if C is equal to 96, we'll have 96 calls to this body function, and the first call to the body function will get I equal to 0, the second one will get I equal to 1, and so on. And this is basically what I meant with the thread example, where each thread only gets one index that it should care about. So in this body function, we get the window from our padded array, and the window will start at index I all the way to n, which was 5 in AlexNet. And once we have the window, we square it. And then here in the denominator, which I defined as d, we compute the sum. So this is einsum notation. And what this notation means is you have the input array, which has channel, height, and width, and we want to sum across the channel dimension. So if the input here has the shape C, H, and W, the output shape should be H and W. And when you define the notation like this, what will happen is you will sum across the channel dimension. Then you multiply this with alpha and add the bias, and in the end, take the exponent of beta. Then you compute the output by taking your original array at index I and divide that by D, and then you return it. And once you have the return, you stack all of them on top of each other, which is what the vmap function does, and return that value. Regarding this slice function, where I said you start at I and go all the way to n, and now you might be saying, well, if I is equal to 6, then I need the kernels from 4 all the way to 8. But in this case, if I is equal to 6, then I would get 6, 7, 8, 9, and 10. But I need 4, 5, 6, 7, and 8. And the reason why this will still work is we're not using our original array, we're using the padded array, which will always have an offset of n integer divided by 2, which means that we always have this offset n divided by 2, and the window will be the correct one. And now that we have defined our local response normalization module, the next thing we need to do is to actually implement the AlexNet model. And I won't be going over each of these layers one by one, because it is simply a matter of calling each layer one at a time, and that's actually not all that complicated. So in order to implement this, all you need to do is basically look at the paper and the layers that they have defined. For example, the first convolutional layer has an input channel of 3 that's coming from your input images, and it outputs 96 channels. Then for the next convolutional layer, the input channels is 96, which you had defined here. The output channels is 256, and so on. One thing I would like to mention is because our dataset has only 2 classes, we will return only a single value. And that value will be the probability that determines if the input image is a cat or a dog. And here in the call method, you can see we have here our feature extractor. That's all the convolutional layers as well as the max pooling layers. And then over here we have the classifier. And one thing to note, this is JAX specific, is we need to pass it a key, because dropout, since this is a layer that involves randomness, it actually needs a key. Next up, we need to define our loss function. And to do that, we pass it our model as the first argument, because that's what we want to take the gradients of. Then we give it the training data as well as a key for the dropout operation. We get the logits from our model by calling the vmap function, because we have here a batch of training data. And to compute the loss, we use this sigmoid binary cross entropy function. And the reason we use that is, well, as mentioned before, our output will be just a single value. And this function will take that single value, compute the sigmoid, which is basically turning it into a probability, and then compute the loss. Basically, if the probability is closer to 0, it will treat it as, I think it was a dog. And if it's closer to 1, then it will treat it as a cat. Finally, we return the loss as well as the logits. And if you remember from a previous episode where I said the loss function should only return a single value, then why are we returning also these logits here? And the reason for that is later when we want to compute the accuracy, we will actually need these logits. And if we didn't return them here, then what we would have to do is to once again pass our training data or the data in general through the network to get these logits. So we would basically have to pass the same data twice through the network, and that would be very inefficient. So it's better to return it here as auxiliary data and use that for future computations. Then we also define the step function, and this is very close to JAX boilerplate code. We give it the network as well as the training data, also the optimizer state, and a key for the dropout operation. Then we call the filter value and grad function, which will return the gradients as well as the loss value. And here we actually get the logits as well, and we get those if we define this has auxiliary keyword as true. And this is just standard JAX stuff right here. So you compute the updates and then you apply those updates. And finally, you return everything. In this cell, we're using the train metrics, which we use from the common loop utils from Google. And I just quickly wanted to give you an example of how this metrics object works. So as you can see, we have here two fields defined, loss and accuracy. And it doesn't matter what you call these, but in this example, it makes sense to call this loss and this one is accuracy. And then we define these as this average from output, and this other one is accuracy. Once we've defined it like this, the question is, well, how do we actually use this? So what we first need to do is to initialize the empty metrics and then use this merge function. The merge function is kind of like what you would do with list.append, where you add an extra element to a list. In this case, it's kind of like that, but not exactly, of course. And for this merge function, we need to pass it another object of this train metrics. And the way we pass it is we use this single from model output. There are other ways you can do this, but this one is, in my opinion, the most simple one. And as you can see, we're passing it 3 keywords. Now you might be wondering, why are we doing this? Why are we passing exactly 3? We only have 2 fields over here. And the reason for that is that, for one, this accuracy class requires that you give it both the labels as well as the logits as keywords. So at the very least, if we have this accuracy right here, we have to pass it logits and labels. Then what about this loss? Well, it says here from output, and then we define this loss string. And when we do that, this function right here expects that you pass it a keyword with this exact name. So we have to give it the loss here. And then under the hood, because this is computing the average, it will, well, compute the average. And if we run this, we can see we have loss and accuracy, and these refer to the loss and accuracy over here. And it computed the loss and the accuracy. The loss here being the average of 3.3 and 2.2. And here the accuracy is computed from these logits and these labels. And just to show you that you can name this whatever you want, let's just name this something else. And if we run this now, you can see it still computed everything. And this time we had to pass it this other string here. So let's move this back to being the loss and continue. For every machine learning task, you will need the evaluation method, which computes the performance of your model against a test dataset. So here, as you can see, we need to reshape it to be a single vector because that's what CLU likes. And then we compute the loss and also get the logits from the loss function. And once we have those, we pass them here to the evaluation metrics. And again, this is the same thing we had defined earlier. And in the end, we return those metrics. And here we start the actual training process. So we need the train metrics, which we will fill up with the values from our training run. We define the model, we define a learning rate, and if this learning rate is not small enough, your network won't actually learn anything, so make sure that it is small enough. The optimizer that we're using is the Atom optimizer, and we initialize it using this filter method. And this was also something I talked about in previous episodes. We're also going to need a key that we will split for every dataset to use for the dropout operations. We define 10 epochs, and here we have this p bar, and that's basically just to make the training run look better. And for that, we will use the TQDM library. We pass it the training dataset and also a description. And here we iterate over the training dataset. Again, we reshape it, and that's for CLU as well. We call the step function and get the updated model, the updated optimizer state, as well as the loss and the logits. And here we add a new train metrics to our train metrics object, and we compute the values from our current train metrics to display the performance of our network. Finally, we evaluate the model against the test dataset and print those values out as well. And depending on your hardware, this may or may not be as fast or slow. In my case, it's a 3090, so it's okay-ish fast. And as you can see, the accuracy does increase. And after the first run over the train data, it will compute the performance of the network on the test dataset. And for the test dataset, the accuracy is 67%, clearly showing that the network is improving. And here I've got an unfortunate error where it says that the memory of my GPU ran out, and that's probably because of the batch size that I chose, which was 64. So if I reduce the batch size, I don't think I will get the error again. So let me just quickly change this to a smaller number. So now I've started a training run with a smaller batch size, and this time I don't think I should get the out of memory error. So here, after 5 epochs, we have a test accuracy of 75%, clearly showing that the AlexNet architecture is able to learn this dataset. So that was it for this video. I really hope you enjoyed it. Thanks for watching, and I will see you in the next one.